Okay, welcome back. We're talking about the concurrency issue. So here's some examples of how the database actually runs. This is not a concurrency problem. It's just a demonstration. So some users pulled up row 100, has read the row, modified it, and wrote it back. Some other user is pulled up row 200, has read 200 and wrote it back. But the way this thing operates in the database is not sequential. It doesn't do all of user A's requests and then all of user B. They're mixed together. So we're reading things out of order. Well, not from user A's perspective, everything is in order. User B's, but it gets processed in different orders, which means when you're talking about the same item, now we've got problems. So I'm reading item 100, you're reading item 100. So the item count is currently at 10. I want to reduce it down by 5, and you want to reduce it down by 3. So in other words, my customer ordered 5 of these, so I need to reduce the inventory. Your customer ordered 3 of these, so they have to reduce the inventory, and so I write the item. But see how these things are all done together? So I set the item, and then I write it, and then I set the item, and then so whoa. I lost an update because when they read this one and set it to 7, I've lost the one where it was supposed to have gone down to 5. Okay, it kind of makes sense. Okay, so the next topic is about these things called explicit locks. Now, I've already mentioned to you that this is a very good discussion behind the scenes, but typically normal modern databases probably do not use the lock keyword. Okay, I'm just telling you. But here they are. An exclusive lock. An explicit lock. An explicit lock does use a lock keyword. Okay, and I go in there and say, I want to lock this table. And nobody else can have it at all until I'm done with it. That's okay. An implicit lock. An implicit lock means the system looks at it and goes, I see user A doing this, and I see user B doing this. I think I should do something on my own to make sure that one of these updates is not lost. So user A doesn't use the lock command, user B doesn't use the lock command, but the system looks at it and goes, I think I know what's going on here. So this is a lot better. Can you imagine having, first of all, it's a matter of, is the artificial intelligence, I use that term loosely, is the AI system of the database smarter than the user? Don't answer that question. Yes! Unfortunately, yes. It's been around a while. It knows, okay? Just saying. So yes. Now, you could say, you could give it a hint. You could say, well, I'm getting ready to do this update thing, and I think I need a table lock. Okay, and the machine would go, well, I was going to do a row lock, but okay, if you say so. Right, so you can give it some hints. Okay, good. So lock granularity, we talked about that before. It could be the entire database, but not really. I mean, come on, no one does that. That's dumb. A table, okay. A region, which basically means the stuff that you're working on. Like if I pulled up 5 rows, that's my region. Everybody else can do everything they want, but not in the section that I have. And then a row lock, which means, like in this particular case, all I really needed to protect was row 100. People could be adding or doing, adding row 400 or 401 or 402 all day long. It wouldn't have caused any problems, right? So, of the types of locks, further subdivide to what's called an exclusive lock, which means nobody else can have it at all. Basically, it's mine, leave me alone. I'll let you know when I'm done. Okay? Typically used for writing. In other words, I do an exclusive lock because I'm the only one who can do anything. I'm going to be able to read and write to this thing, and I don't want to be disturbed. And then a shared lock is basically, well, okay, I'm going to be doing some stuff, but you can be reading while I'm doing it. I mean, I don't want you to do any writing during that, but if you want to read it, that'd be okay. All right? So one is like, go away, leave me alone. You can't have nothing because I ain't done yet. And the other is, well, I'm working on this, but if you want to read the table while I'm working on it, okay, not write, but read. All right? Cool. All right. So two-phase locking is how you basically solve this problem. There's a cool little diagram here. So here's the thing where something happens. I lock item 100, and then I read it, and then they try to do a lock, so they can't. Okay? Because I've locked item 100, and when this person comes in and says, hey, I want to lock it, they goes, I'm sorry, you just have to wait. And so it just hangs around. I mean, quite frankly, it's probably not noticeable, the weight involved, okay? So then the red ones go, I set my item, I do this, or release the lock. And then the purple one just picks up right behind it. So user A wasn't impacted at all, and user B had a slight weight, but it's not that big. I mean, we're only talking milliseconds here, right? So probably user B did not know that the lock did not go through immediately, and that they were put on the back burner waiting for user A to do their thing, okay? Pretty cool. All right, two-phase locking. And so the typical way you do this, you have what's called a growing phase, where you obtain the locks that you need, and then a shrinking phase when you release the locks. So every time you do a lock, you're supposed to unlock. I mean, that was kind of absent from here, but hey, it's a pretty cool diagram either way. So, you know, releasing the lock and releasing, so obtaining a lock, releasing a lock, obtaining a lock, releasing a lock. That's basically how it works. Now, there is a scenario where you could get a problem. It's called a deadlock. And I like their example. Their example is the one with pencil and paper. It's a perfect example of this thing. So, I need both paper and pencil. So I lock the paper, and then I take the paper. And then I attempt to do a lock on pencils. But user B is locking pencils, and she takes the pencils and tries to put a lock on paper. So let's go through and see how it worked. So lock on paper, that was successful. Lock on pencils, great. Process A's request for the paper, process B request for writing the pencil, okay. But then I put A in here for waiting for pencils. And then B is waiting for paper. So if I'm waiting on you and you're waiting on me, that's a deadlock. In other words, nothing will ever happen. It'll just stop, because I'm always, you know, user A is always going to be sitting there going, well, I'm waiting for you to release the pencil. And the other one says, well, I've got the pencil. I'm waiting for you to release the paper. So this is a deadlock. And the solution is kind of simple. The solution to prevent a deadlock is to don't ask for a lock on part of your requirements. If user A said, I need a lock on paper and pencils all on line 1, then this problem would have gone away. This person would have said, oh, hang on a second, I'll wait for you to get done. Okay, so the rule is, how to prevent a deadlock is to ask for everything up front, not part of your requirement, all of it. Okay. On page 47, they talk about 2 different ways to solve this problem. And this sounds complicated, but trust me, it's not all that bad. It's called optimistic versus pessimistic locking. Okay, now this is weird, so just bear with me. Optimistic locking says, you know, this database isn't all that lively, and there's not that much stuff going on. So most likely, most transactions are not going to require a lock. So, in optimistic locking, if you choose this technique, the machine actually does not use locks. I'll rephrase this for emphasis. Optimistic locking does not use locks. What? Optimistic locking does not use locks? Yeah, that's what I said. What it does instead is, it says, okay, I'll do the update, okay? And then after the update has happened, I'm going to go back and reread that row a second time and see if anything else changed. In other words, I'm updating the zip code field, okay? And so I do my update, boom, and then the machine goes and rereads that row and sees that the update, that the zip code has changed, but it also notices that the last name has changed. And he goes, whoa, stop. I missed something somewhere. Let me just redo my transaction over a second time. Okay, so it does the update, reads the row, and then decides whether or not it needs to do it again. So if I update the zip code and then I read the row and it's not updated, that means somebody clobbered me. Okay, so it has to, every field has to match. You know, I pull up the old row, And the only thing should be changed is the one field that changed, right? The zip code, nothing else. If something else changed or the zip code field did not happen, then I know it got clobbered. So it's not using a lock at all, but it's an awful lot of processing. Think about this. Has to do an update, and then a select, and then another update afterwards. And it might even go through this several times. You know, like, oops, that didn't work. Oops, that didn't work. Oops, that didn't work. Kind of weird, huh? Okay, so that is optimistic locking. Okay. So the example on page figure 9.9 is horribly misleading, so don't look at that because that'll just confuse you. Pessimistic locking means, look, this is a very lively database, and there's lots of stuff going on here. And so most likely, you know, I don't know, 50% of the things could possibly have some concurrency issues. So I'm going to go ahead and use the locks every single time. Okay. So again, you just tell the database, hey, this is kind of a lazy database, not much activity going on here, not that many inserts and updates. Basically, we're talking inserts and updates, right? Okay. So if you have a database with lots of inserts and updates, then maybe you want to go ahead and use the manual kind of locking, using pessimistic locking. Tells the machine, well, instead of cheating, like optimistic, I'll just go ahead and do locks. So why? Why are there two different ways of doing this? Well, locks are expensive. Okay, doing a lock on the database churns up time and energy and slows things down. So doing something that would prevent you from using locks is always a win. Okay, on the other hand, if you have a very lively database with lots of inserts and lots of updates, well then having to do an update 15 times to get it to work it's going to be worse than using a lock. So you have to kind of decide, do I want to use optimistic or pessimistic? Okay, so the amount of effort involved is what we're trying to get to. You know, which is easier on the machine, doing an update 15 times, or, okay, let's change that. Doing an update 5 times, or doing a lock every single time? Okay, so now, here's the sticky question. Does one of these techniques do a better job than the other to protecting the database from concurrency issues? What do you think? No, they're the same. It doesn't matter if you use optimistic or pessimistic. They would both do an adequate job. So what we're talking about is the amount of resources that the database engine has to put out to be able to accomplish this. You want to reduce the amount of effort the machine has to have to prevent both of them adequately solve the concurrency issue. It's just how much effort do you want to put into it to pull that off. That's what we're after. Okay, on page 471, they start talking about the transaction control language. Remember I always talk about the big 3 SQL categories. Well, okay, this is a 4th one, but unfortunately it's not very standard. You know, every database vendor is basically allowed to do whatever the heck they want. So I don't really call that. So there's a thing called begin trans, and then a commit and a rollback. So I'm going to go to this figure here. Here's an example. Now this is not real honest-to-God code because it's got some programming stuff in it that I don't want to deal with in this course at all, but let me just show you what we're talking about. So I set this thing up to be a beginning of a transaction, which means I have 2 SQL statements that I want to bond together. So if one of them fails, the other one fails, right? It's all or nothing. Remember all that? Okay, so here I'm setting up something where I have, you know, select the old quantity, you know, from whatever, and then I take the new quantity and take the old quantity minus 5. And then I turn right around and do an update of some sort. So this pulls the data to grab the current inventory amount, decrements it by 5, and then updates that record. So that's 2 SQL statements, but I want them to all or nothing. I want to bond them together in a single transaction. Okay, we'll continue this discussion in just a minute.